All right, so optimization problems. So the first step there is to understand the problem. All right, what do I mean by understand the problem? You need to read carefully because this usually come in the form of problems. All right, it will not just be an equation that will give you a say solve for x or integrate. No, it's going to be a word problem. So you need to read carefully and understand the problem. All right, and when I talk about understanding the problem, what do I mean? So if you notice there, they say read the problem carefully until it is clearly understood. Ask the following question. You ask yourself, what is the unknown? So you want to find out what the unknown is, right? And then what are the given quantities? So what do you know? All right. So what have you been given? All right, and what are the conditions? So this condition is very important. All right, so most of the time I'll give you an optimization problem, but I'll tell you something. I'll give you some useful information that can help you to model the question. All right, to come up with nice equations where you can solve the problem. But at the same time, you should be able to ask yourself, what exactly am I asking you? Because if you don't know what I'm asking you, then what are you solving for? All right. And then the condition, there's a restriction. So I will tell you, for example, I'm going to say maybe I have a little balloon and A's live in the balloon, but then I'm going to restrict you on what maybe the radius of the balloon at the end of the day is supposed to be. So you need to read carefully what are the conditions. It's not enough to only know what have been given, what are you looking for. You need to understand the circumstances, all the restrictions, right? And then look at step two there. I know this is a one that people hate because you guys, some of you suck at diagrams, but just draw a diagram. It doesn't have to be the most fancy diagram in the world. Why do I need a diagram? I need to see that you understand what I'm asking you. A wrong diagram, what does that mean? It means clearly you don't even understand the question. If you draw a nice diagram, you label it nicely, then I know you are on the right track or you know what you're doing. At least you're going to get a method mark, right? So please draw a diagram as where possible. I would say that always draw a diagram. All right, that's just what I'm going to say. Unless the question is too clear enough that the diagram is not necessary. But for most cases, you have to draw a diagram to see exactly what is happening. And then introduce notation. So use symbols, all right? So most of the time I'll be asking you to maximize or minimize something. We talk of optimization, there's only two things there. It's either you maximize something or you minimize it, all right? But let introduce variables. Yeah, I use the word symbol, all right? For example, volume, you can call it V. Radius, you can say R, and so on, all right? If you don't explicitly define your variables, then I'm going to consider that you're making use of standard variables. When I use the word standard, it means, for example, V for volume is fine, R for radius is fine, T for time is fine, H for height is fine. The minute you start doing stuff like, let's say, dk dt of, I'm going to say could the k and now actually what is k in this case, all right? So please, if you use any funny symbols and variables, just tell me what they are, what you're trying to do, all right? I'm not restricting you to specific variables and symbols, but tell me what you're doing. If you don't tell me, I'm using standard variables, all right? I mark it as standard variables. And then for 4, they say express Q, so that symbol you have, in terms of some other symbols. So where we do an example, I'm going to explain step 4. We're going to go step by step. And then step 5, they say that Q is expressed as a function of more than one variable. This is very important. You notice that most of the time, the information you have or that symbol you have Q, it will be expressed in more than one variable. But you know that to successfully find the derivative of a function that contains more than one variable, the first you need to try and do is to eliminate one variable, right? So the whole idea about step 5 is to try and eliminate one of the variables, all right? And then once you do that, get the domain, right? Like I said, when we do an example, I'm going to go step by step so that you see how it works. And then once you do that, obviously, to find absolute max and mean, most of the time we use something called closed interval method. We've discussed that already, right? So if I tell you to minimize something, it means you finding the absolute minimum. If I say maximize something, you find the absolute maximum, all right? Hence, using the closed interval method. And how do you get that closed interval? You see, is by looking at the domain of that function, all right, that you're trying to minimize or maximize. Once you get the domain of that function, you're going to see what the restriction is, all right? Let's look at example one. So example one, I'm just going to highlight the key term here. They say a farmer has 1,200 meters of fencing, right? So there you just underline the key term there, 1,200 meters of fencing, okay? And wants to fence of a rectangular field, all right? So I give you a shape, I say rectangular, right? So in mind, you know that you're dealing with a rectangular shape that borders a straight river, right? So in your mind, I have some rectangular shape and there is some sort of river that actually passes there. So it borders a river, there's a river there, right? I'll just use this for river. So there's a river. And they tell me they have 1,200 meters of fences. So it means this total distance here, this whole length here is 1,200 meters. Mathematically, we say that's just the perimeter, right, of your rectangle. So you see, just by doing a little sketch, it tells you already, it gives you so much information, all right? And then now ask yourself, what exactly am I asking this question? I say he needs no fence along the river. So it means that your focus, let me just change the color. So your focus is this. So you're just looking at this, all right? So along the river here, you don't need any fencing. Obviously, for someone to come into your farm, they have to swim through that river, which obviously that is an insane task, all right? And then I ask you, what are the dimensions of the field that has the largest area? I'm asking for dimensions. Dimensions for a rectangle, in this case, it will be, you can say length times width. So, and then I need the largest area. So that dimension needs to give me the largest area. All right, let's do this step by step. Let's assume that we don't know the length and the width of a rectangle. So I just put an on there. I'll just say this distance is x, and this distance on the top, there's y. You see already just by doing this, it tells me that the total, so x plus y plus x dash perimeter is equal to that 1,200. All right, there I have two unknowns, it's fine. But also there's another equation I can get, which is just the area of a rectangle is length times width. You see two equations with two unknowns, you're good to go, right? Because you can easily eliminate one variable. So that's the whole idea about optimization. So let's jump to the memo quickly. All right, so there's a solution there at the top. So this was exactly what I was saying. So you just focus in. So your focus is just on these pieces. So the x, the y, and the x. All right. So you don't really care about what happens along the river. The first thing you have there is just the area of a rectangle. What is area of a rectangle? It's length times x times y. All right. And the perimeter, because I tell you the total length of fences, so total amount of fencing you want is 1,200. It means you need to sum the sides. And just to mention, it doesn't matter the leveling. Me, I use x, and y there. You can swap it around and use maybe y there and y here and x there instead. It's fine. So it doesn't actually change your final answer, right? So that's just labeling. Now, if I have two equations, you see, so what have I been given? I've been given perimeter, all right? What am I looking for? I'm looking for dimensions. I'm looking for that xy that will give me maximum area. So that means I need to know what the area is, all right? And if you have two equations and two unknown, it's fine because what happens? You can eliminate one of the variables, all right? You trying to to maximize the area. So always keep in mind, what are you maximizing the area? You want the dimensions that gives you the largest area. So indirectly, what are you doing? You're trying to maximize. The word largest area means maximize the area, right? If I say minimize area, it means you minimizing area. It means you're going to look for the absolute mean. So in this case, look at this equation here, 2x plus y equals to 1,200. Obviously, I can make y the subject, and I can write my area entirely in terms of a single variable. So this is something that you must get used to. What am I trying to maximize or minimize? In this case, it's area. But look at the area. It's in terms of two variables. I need to eliminate one of the variable. What other equation do I know? That is when it comes down to what have you been given. There's a perimeter now, you see. And by eliminating the variable, you end up with your area in terms of a single variable. And once you hit this step, this is where we now go to that restriction that was talking about. If you equate this area to be equal to 0, you solve for x. You're going to see that x typically is 0 or 600. So x needs to lie between 0 and 600. All right. This already is that closed interval that we work with. It means we can apply closed interval method. All right. If you have an area that when you equate to 0, you can actually solve for x, then in that case, let's assume that it was a polynomial, but you can actually factorize it. Then you have no restriction. It means closed interval method does not work. So keep in mind that it's not always the case that when you try to solve an optimization problem, you have to use closed interval method. Closed interval method works when you have a function which is continuous on some closed interval. All right. So in this case, we can apply closed interval method. Why? Because this function, the area function, which is now in terms of a single variable, gave us a restriction. It's x between 0 and 600, right? And you know how to get it. Just equate that to be equal to 0. Get x is just 0 or 600. So that's the restriction. It means x has to be between 0 and 600. And obviously, for closed interval method, first thing, you get the first derivative. Find critical value, so you equate it to 0. Your first derivative to 0, you just get x to be 300. If you know x, obviously remember there's this equation there for the perimeter that links x and y. It means you can solve for y. So x is 300 if you solve for y, y is 600. All right, don't stop there because I need to see that that area you have is actually the maximum. All right, so we have, you evaluate the area at the endpoint. Remember what closed interval method says. Evaluate the function at the endpoint. In this case, the function is the area function at the endpoint. So area at 0 is just 0 because if you plug 0 in this area formula, you just get 0. If you plug area at 300, remember x here we solve is 300, and 300 is fine because it lies within that closed interval. You get 180,000 meters, which is good, all right? And if you find the area at 600, which is this other endpoint there, you get that is 0. So it makes sense to see that the largest value is the area at 300. It means this x value actually gave you the largest possible area. All right? It means you've done a very good job. Hence, you say my rectangular field should be 300 meters deep and 600 meters wide. All right. Or you can just say the rectangular field has to be 300 meters by 600 meters. All right. If everyone is happy with question 1, let's move on to solve another optimization problem. So let's look at the second example. Now, example 2, they say cylindrical can. Cylindrical can. You see there I give you a shape now. So what do? You highlight the shape. I have a cylindrical can. So I'm dealing with the cylinder there, right? I'm dealing there with the cylinder. It's made to hold 1 liter. All right, so 1 liter, just for the record, 1 liter of oil. In this case, I'm talking of 1,000 m cube. Right? If you use 1,000 cm cube, it's still fine. I'll give you the max. But I will try to be unambiguous in my test. So it means that I'll give you stuff you can work with, not something that you have to think again extra. So for this specific example from the textbook, they just say 1 liter for you to interpret what 1 liter actually stands for. All right. So 1 liter there, you can just say 1000 cm cube. All right. Then they say find the dimensions that will minimize. Remember example 1, we're maximizing this one. They're not asking you to minimize. All right. So you want to minimize the cost of the metal to manufacture the can. Okay, so it's a cylinder. That's the first thing you know. So you know your can is going to look like that. Okay, my can looks terrible, but make sure you draw a better can. So that's the can. How can you minimize the cost of manufacturing this can? Do you agree that is by minimizing the area? Do you agree? Because if someone uses this can to store 1 liter of oil, let's assume that that 1 liter fits up to that point there. You see, there's a lot of empty space at the top. It means you're wasting money. All right. Another person who designed their can with a smaller area such that that 1 liter fits nicely. And that person is doing what? He's minimizing the cost. So 1 liter fixed there up to the top. There we go. So you see that the interpretation here is you trying to minimize the cost of the metal to manufacture the can. Indirectly means that you're trying to minimize the area of the can. All right. Because if you use a very big can that can hold 2 liters of oil, that's not optimization because you're wasting can or metal space. All right. So you need to manufacture the can so that it holds exactly 1 liter of oil. All right. So let's jump to the solution. All right. So look at the diagram that I have there. I'm going to explain why I have this piece by piece. All right. So we want to minimize the area of a can, and that can is a cylinder. It means that we need to be able to compute what we call the total surface area, right? Total surface area. And for you to be able to do that, you need to realize that this can needs to be cut into pieces for you to be able to compute that total surface area. And what are the pieces? The first piece you see there is this guy there at the top. There's a circular piece at the top. There's a circular piece at the bottom. There you go. That's why I have these two there, two circular pieces. And then this side, this is what we call the lateral area. Very important. Please remember the word lateral. I'm sure you will see somewhere in your assignment as well. All right. Lateral area. So this piece is lateral area. All right. So the word lateral area just means if I chop the top off, I chop the bottom circle off, the side. So if I open wide that can, I just have what we call the lateral area. So remember that word. And for this lateral area, what do you observe? If I cut this can, so if I cut it there, notice that if you stretch it open, it actually becomes rectangular. But now the good part is we know that for rectangle, you have some sort of height there, and then that long distance is just the circumference of a circle. Remember that the top initially was circular. So obviously, if you have to compute that this total distance here of your circular top piece is just called circumference. It's 2 pi r, right? With this in mind, means now you're ready to compute your surface area. Notice it, the area of a circle, pi r squared, pi r squared. How many of them are there? 2. That's why I have 2 pi r squared. Let's come to this piece. Well, how do we compute the area of this piece? You know it's going to be this height times the circumference. So 2 pi r times height. There we go. Then the next information, I told you that that can needs to hold 1 liter of oil. Like I said, 1 liter, we just use 1000 cm cube. So in this case, what is the volume? You see, you ask yourself now, we're dealing with a cylindrical cylinder. What's the volume of that? The volume of a cylinder is area of this circular piece times the height. That's the volume. So it's going to be area of the top piece is just area of a circle. Pi r squared times the height, which is h. And what volume did I give you? I give you 1 liter, which is 1000 cm cube. All right. And now ask yourself, I want to minimize area, but my area has two unknowns. It has the radius and the height. Like I said, you need to always eliminate one variable, then you're good to go. So how do I eliminate? I use that information that was given, all right, the volume. So if I make h the subject, I just have h is 1000 over pi r squared, and substituting my a, you can see my a, I can write it entirely in terms of r, is going to be 2 pi r squared. 2 pi r in the place of h, I just put in that 1000 over pi r squared. Simplify, you get something that looks like this. Now, if you look at this closely, we don't use closed interval method. I'm going to explain why. I told you that once you get this equation or formula that you're trying to optimize, I said try to see if you can equate it to 0 and solve for the unknown. If you try to solve this particular equation, you notice that r there will be negative because you end up with some r cubed equals to minus something. So you're going to get negative value, which doesn't make sense, right? Because you can design a cylindrical can with a negative edge. So you need to think further now, okay? The fact that I can't equate this to 0 because I'm going to get some negative result. What else can I do as a restriction? The bottom piece here cannot be 0, by the way. It makes sense, right? Because you can say that I design a can with 0 radius. It doesn't make sense. So my only restriction is just that that radius just has to be bigger than 0. All right. Because if the radius equals to 0, it means you haven't designed any can in the first place. All right. So you just want r to be greater than 0. Keep in mind, this is not a closed interval, means we're not applying closed interval method here. So be very careful. So this is an example where we're still solving optimization. It's an optimization problem, but we're not using closed interval method. All right. I hope that makes sense. All right. And what's the difference between this and the previous example? Is that at this step in the previous example, we had a closed interval. But in this case, we can't have the closed interval. All right. We just have the restriction r is greater than 0. Now, as usual, get your first derivative. Please simplify as much as possible. Factor out common terms. And then obviously you want to see where that first derivative equals to 0. So you want those critical points. You get your r there to just be the cube root of 500 over pi. And if you notice at this step here, if you don't understand what's happening, it's just me putting this r on a number line and testing the sign. All right. So I'm trying to find a minimum. So the first thing I need to be able to observe is this kind of shape. That on the left of that arrow value is typically decreasing, and on the right is actually increasing. All right. And you know, when you have this shape, you're talking of minimum. All right. I hope that makes sense. That is what I'm saying here. That the area is negative for arrow less than, for values of arrow less than this value that we have here, which is that shape that you see. That means it's typically decreasing. And then the area is greater than 0. I mean, that is positive for arrow bigger than our arrow value that we have. It means there's positive, it means it's increasing. And already that shape there tells me that it's a minimum. All right. Therefore, we can say the area at arrow, evaluated at arrow, is an absolute minimum. You see, we came to the same conclusion, but not by using the closed interval method. And if you try to compute complete h, so where you see r there, you put in that cube root of 500 over pi. Notice h just becomes 2r. So it means that design your can such that the height is 2 times the radius. All right, that's just a summary of this question. So please, like I said before, it's not every optimization question that you have to use closed interval method. But if you see that you can apply closed interval method, then go on ahead and use closed interval method. All right, let's move on. Example 3. And like I said, please ask questions if you don't understand anything. All right, because like I said, your assignment, you should be able to understand what I'm doing to the thesis before you'll be able to get any mark out of your assignment. All right. So if you don't understand what I'm doing here, then the optimization problem there, you will not be able to tackle it. All right. So let's look at another possible optimization question. Yes, this is a very nice one. Let's find the point on the parabola that is closest to this point. Right. I'm going to show you something exciting really quickly. So, is that pencil? All right. So the first thing you notice is I have a parabola. So I'm going to have this kind of shape. You know, something that looks like that. Please know how to sketch your diagrams. Because like I said, for optimization course, I need to see a diagram. Right. So know how to sketch your diagram. All right. So I need to find the point on the parabola. So that parabola that is closest to the point 1, 4. The first thing you observe is, let's assume that this is 1 here. So x is 1 there. If you plot 1 in this parabola, what do you get? You get y squared equals to 2. And if you make y the subject, you just have y as root of 2, and you know root of 2 is typically 1 point something, right? So let's assume that that is root of 2, somewhere there at the top, root of 2. So if I just plug in the point 1 on that function, this is where I'm going to land. But look at the point that I gave you that you're working with. It's 1 and 4. So it's something completely out of it. So it's sitting right there at the top. It's a completely different point. So the point 1, 4 is now right up there. So this is 4. All right. So indirectly, what I'm asking is, walk along this parabola. So find a point along this parabola so that the distance, so let's assume that that point is something there that we don't know. We call it xy. So it has some xy coordinate. So that this distance here is a minimum. So I need the point in the parabola that gives me the smallest distance to this point. I agree that point cannot be this one here, 1 and root 2. Because this distance already, just by looking at it from there to there, is much longer than this one that I drew here. Right. So you see, so it cannot be 1 and root 2. Hence, that's why we need optimization. So there's some unknown point there. You can call it xy. All right. Just call it xy. Right? And then you ask yourself, okay, I'm given a parabola, I know what the sketch looks like. How do I find the distance between 2 points? Do you agree that is grade 10 stuff, right? Because you guys know it's just square root x2 minus x1 squared plus y2 minus y1 squared. You see, you still need to remember your grade 10 stuff, all right? So let's just jump straight to the solution so that I explain again step by step. There you go. All right. Let me get my pencil again. So you see what I was saying? So there is some unknown point there, xy, that the distance is going to give us that minimum d. So the distance is the smallest. So we don't know what that point xy is. We're trying to find that point xy. First thing is to compute distance. You know that distance is just square root x2 minus x1 squared plus y2 minus y1 squared. But now you know what x1 and y1 is because I gave you a point as a reference. So there you have 1 and 4. So you have x minus x1, x1 is 1 in this case, and plus y minus y1, y1 is 4. So if you use that point, 1, 4, you end up with this second step here. All right. Now, what did I say? You're trying to minimize what? Distance, d. All right. But now look at it, there's still 2 unknowns. As usual, we need to try and eliminate one of the variables. You see, it's a routine process now. We're now getting used to the process. Is that you get that equation you're trying to minimize or maximize, and it is having 2 unknowns, and then you try to eliminate one of the variables and then find the first derivative. So let's try again and eliminate one of the unknowns there. But how do I do that? That's the question. You ask yourself, what equation do I know? What other equation do I know except equation of distance? Obviously, it's the equation of the parabola itself that I gave you. I gave you the equation of the parabola, and it links the 2 variables that you're working with, x and y. Therefore, that's a good place to start. Now, the choice of what do I make the subject? You see, that's a very important question here. Ask yourself, is it easier to make y the subject? Is it easier to make x the subject? The answer is it doesn't really matter in this case. All right, you can make y the subject, so you can say y equals to square root of 2x. Remember, I'm not using the minus root of 2x because the point is up there. The point can be somewhere down here. Why? Because that distance from this point all the way to 1, 4 is going to be very long. And we just want the shortest distance. So it's obvious that it's going to be on top here. And in that case, it's just the positive side of the root. So if you choose to make y the subject, it's fine. But remember that instead of saying plus or minus root of 2x, you're just going to say root of 2x because it has to be on the top, the positive part of your parabola. But for my solution, to eliminate any doubts which side is positive, which side is negative, why not just make x the subject? You see, it makes life easy. If I make x the subject in this parabola, I just get x is y squared over 2. You see, I don't need to care if it's positive or negative. That's why I say, please make good choices when it comes to eliminating one of the variables. In this case, I make x the subject, so my whole d, the distance formula, is now entirely in terms of y, which is good. It means that I'm getting close and closer to what I'm trying to achieve. If you square both sides, d squared, this function that we're trying to minimize, that distance function we're trying to minimize, you instead of calling d squared, you can give it a fancy name. You can just say f of y, all right? Where f is just some function, it's still a distant function. The y they just say is in terms of a single variable y, all right? Why? It doesn't make a difference if that function I'm trying to optimize has a root or not. That's why I start by squaring it and then just see that this d squared, we can just call it a function in terms of y. All right. And looking at this, if you try to solve as usual, notice that you're not going to get any fancy value for y. All right. So it's not something that you can actually solve for y. Hence, looking at it as a polynomial, what other restriction do we see? There's no restriction because it is a polynomial. Therefore, y is an element of real number. I told you guys, once you hit this step here, where that equation, that function is in terms of a single variable, and you can actually equate it to 0, or when you try to solve it, you get no solution, then look at it closely and see if you can spot any restriction. If not, then just give me what the domain is. All right. If you remember where we talked about domain when I was giving you the guidelines on optimization. In this case, the domain is just y is an element of a real number because it's a polynomial. All right. So, quick question: are we going to use closed interval method? Can someone just answer that? I believe someone understands what to say. Can we use closed interval method here? All right, someone said no. That is true. Can you say why? Why can't we use closed interval method? You can unmute yourself and talk just to save time. So I accept that we can use closed interval method, but the question is why not? Why it doesn't work here? All right, looks like you guys are not confident of your reason. The reason is this guy there. All right. For you to use closed interval method, there should be a closed interval to work with in the first place. But look at this, x or y element of real number. What does that mean? There we go. This same student gave me the correct answer. The parabola doesn't have, so there's no restriction there. All right. Okay, not necessarily the power. Okay, that distance equation that doesn't come with restriction. All right. So there's no closed interval. All right. Because y is an element of real number, it means y can be any number. It makes sense because look at the diagram. This thing can extend forever. All right. So you can have any possible y value. You don't have any restriction. All right. If you find the first derivative, if you simplify nicely, you get this. It's just y cubed minus 8, right? And if you equate it to 0, your critical value there is just 2. Obviously, if you know what y is, using the equation of the parabola, you have x is 2, right? Now, don't tell me that y is 2, x is 2, you're done, all right? What did I ask you? I said the point on the parabola that is closest to that point. I need a point. So you need to give me in coordinate form. All right, give me as a tuple, 2, 2. There we go. Give me in coordinate form. That's the point. So the point on the parabola closest to 1, 4 is 2, 2. All right. This extra piece is just a bonus. The distance is root of 5. So if I ask you for the point and the distance, obviously give me both of this, but for this question, this is just what I'm going to focus on. All right, is going to be 2, 2. All right, and obviously because you only have one possible y value to work with and one possible x value to get, all the distance you have there is root of 5. Therefore, this one x value, definitely they are going to give you a minimum. All right, we call it absolute minimum. All right. The only time you ask yourself or you doubt if you're going to get is this distance actually a minimum or not, all right, is when you have multiple critical values to work with in the first place. For those of you that like to show me all the extra hidden steps, take that y, put it on your axis there, so put a 2 there, test the sign, notice that you're going to get that kind of shape. It's going to be decreasing there, is going to be increasing there. All right, let's see why. Choose a value less than 2. So let's take 1. When I put 1 here in this equation, y cubed minus 8, what happened? I get negative answer. What does negative answer mean? Decreasing. If I choose a value bigger than 2, let's use maybe 3. If I put 3 in this equation there for first derivative, what happened? I get 27 minus 8. You see, it's a positive result. Just by you indicating this on the side, it tells me that you know what you're doing. It's a minimum. All right. That's why that result you have is a minimum. So you want the point closest. You want the minimum, the absolute minimum, the smallest possible distance. And this little diagram that I drew here shows you that it is actually a minimum. All right. If you quickly put it on the number line and it's the opposite way in there, it means that there's something wrong with your result. All right. Please always check to see that you get a minimum. Take that critical value you have, put it on the number line, see if you get a minimum when I ask you to minimize, see if you get a maximum if I ask you to maximize. All right. Let's look at our last example. All right, example 4. They say find the area of the largest rectangle that can be inscribed in a semicircle of radius r. Semicircle. All right. So let's see. Find the area of the largest. So let me get my notation. Largest rectangle. Largest. Maximizing. It has to be inscribed. Means that I should be able to fit it nicely. Why am I fitting inside? I'm putting inside a semicircle. Not a circle, a semicircle. Some of you actually say, what is a semicircle? Semicircle, just take a circle and chop it into half. You get a semicircle. So take a full circle, chop it into half, you're done. So in this case, let's assume that that is my semicircle. Like I said, it doesn't matter. Another student can choose to draw this at the bottom here. It's still fine. It's still a semicircle. All right. We'll still end up with the same result. So let's assume I'm working with this. I need to fit in some rectangle in there. And do you agree that depending on the dimensions of this rectangle, I might get the largest possible area, I might get an area that is not the largest area. I'll show you quickly. Let's say now another student choose to do this. That is their rectangle. Do you agree those dimensions are not exactly the same? There's infinite possibilities. Another student can actually do this. All right, but the question you ask yourself is, how do I actually get the rectangle that fits inside this semicircle, but at the same time gives me the largest possible area? Because the area has to be the largest possible area. All right, so let's jump to the solution quickly. So in the solution, let me just go down. So here I mentioned that a semicircle, so I choose to use the upper half, right? Like I said, there's no strict restriction. You can use the lower half. A semicircle is just half, all right? So it can be the upper half or the lower half, or you can choose to draw it entirely facing this side, all right? But you must keep in mind that depending on how you draw your semicircle, your computation might be a little bit more difficult. So the easiest one is to do this one. So just draw it as the upper half. Now, because I use the word semicircle means that it's very important that you know that you've been given one equation already, which is the equation of a circle. X squared plus y squared equals to r squared. That's just a general equation of a circle at the center of the origin. But like I said, we're focusing on the top piece only. That makes it a semicircle. All right. It doesn't mean that because we're chopping into half, you're going to take this equation of a circle and divide it by 2. No. The general equation still stays the same. All right. Now, I have the equation for my semicircle. I'm trying to maximize what? You see, that's the question mark yourself. What am I trying to maximize? The area of a rectangle. So let's assume that is the rectangle that you have in there. You just need to label the size. So you see there, I call this X, I call this other side X, and this height I call it Y, this other height I call it Y. All right. So what now is my area of this rectangle? So what am I maximizing the area? So I need to be able to compute the area. The area is a length times the width. What's the length? You see the two of those x there. So it becomes 2x times y, just one y. All right. So be careful. Don't say 2x times 2y. No, it's just 2x times y. That's the area. So I know my area. I know the general equation for my semicircle. I'm good to go because this is what I'm trying to maximize. Therefore, I just need to eliminate one of the variable. You see, in this case, I can make y the subject and y will just be square root r squared minus x squared. Notice it, I didn't say plus or minus because I'm using the top piece. So I'm using the semicircle there, the upper half. The upper half is just positive. So if another person using the lower half there, you're going to use the minus square root. All right. But like I said, you still end up with the same answer. So my area in terms of a single variable now, x is going to be 2x times y, where this is y. Now ask yourself, if I equate this to 0, notice it, I can get x equals to 0, and I can get x equals to r. What does that mean? I have a restriction. There we go. You see in the previous examples, we couldn't solve. You can't factorize, you can't solve for the variable, all right? And we just look for any restriction. If there's no restriction, we state the domain. In this case, if I equate this to 0, I get x is 0, and if you equate that square root to 0, you get x equals to the radius. So in that case, you are restricted, all right? So your restriction now is between 0 and r, all right? Sorry for that. It looks like the network went down a little bit. Can you guys still hear me? All right. I'm very glad you hear me because I think on campus we have power problems here. But yeah, let's continue. So now that you have this closed interval, do you agree that we're going to use closed interval method because of that? You see, that tells you the closed interval method. That's the meaning, closed interval method. All right. So closed interval method, obviously, first derivative, like I said, write everything as a single function. So your derivative, write it as a single function. And if you do that, you just need to equate it to 0 and find critical values. If you equate this to 0, the only way this rational function can be equal to 0, I use the word rational because it's some function over some function, but you must that remains an algebraic function because there's a nice root at the bottom. So the only way this algebraic function can be equal to 0 is if this top piece here, is equal to 0 because you don't want your bottom function to be equal to 0. And if you equate that top function to be equal to 0, x is plus or minus the radius over root 2. Now, notice it, because of this closed interval, you're going to check, can x be negative? No. You see, x has to be between 0 and r. So you can't tell me that x is negative r over root 2. It doesn't make sense. All right? So my conclusion is that therefore x equals to r over root 2 because look at that, x needs to be greater than or equal to 0. All right? My reference is there. All right? So x cannot be negative. It's as easy as that. All right? And if you look at the diagram itself, look at what x looks like. This is x, right? You see that it has to be somewhere between 0 and r, no matter what kind of shape you choose to draw for your rectangle inside there. It will always be between 0 and r. All right. So even if you end up making a mistake with this area function here, go back and look at your diagram. Does it make sense to say that x is between 0 and r here? You can see that there is a 0 there at the origin, and then there's r there. So this x that the label here has to be between 0 and r. So it makes sense. So if you give me a closed interval, look at your diagram and see that closed interval you're giving me makes sense. All right, always go and check. So in this case, we eliminate the negative value for x, then we apply our closed interval method. So you evaluate the area at the endpoint, which is 0, and at r, notice that you get 0 as output. You don't want your rectangle to have an area of 0. So what's the next thing to do? Evaluate your area at the critical value, and there's only one, which is r over root 2. If you simplify that, you do all the math, you just end with r squared, right? And that is your absolute maximum value. You're good to go, all right? So your dimension for your rectangle in this case, remember you need x plus x, so you need 2x. So do you agree it will just be 2r over root 2? All right. And then how do you get y? You get y just using this equation here. There you go. But in the equation, all right, someone says, so said, just to confirm, so you're saying that we use closed interval method if there is a restriction. The answer is yes, all right? Because you can see that x is an element of real number, all right? You cannot do that. Why? Because if you look at this diagram, there is a restriction. So this semicircle that you have here restricts you on what that rectangle is going to look like, all right? You know that this x that you have here, it has to lie between 0 and r. But keep in mind that this restriction I have here, I got it just by writing that equation of area in terms of a single variable and just equating it to 0. I can already get the endpoints of my restriction. All right. So sometimes you can get the restriction by looking at the diagram itself, or you can get it by calculation. All right. So yes, if you have a restriction, you get closed interval method. But I don't want to just say restriction, because even in the other example where we say arrow needed to be greater than 0, all right? Keep in mind that arrow greater than 0 is still called a restriction. It means that arrow cannot be 0 or less. But we don't apply closed interval method. So in summary, we use closed interval method when our restriction is a closed interval. All right. I hope that now makes sense. So your restriction has to be within a closed interval. That is when you apply closed interval method. When I say closed interval, we're looking at something like this. So you have some A there, and then you have a B, which are included. So endpoints are included. So this is closed interval. All right. If your restriction is the set of real numbers, no closed interval method. If your restriction is something like this, it goes all the way to infinity, no closed interval. But if you have something like this one that we're working with, this less or equals to this symbols you see here is a sign of including the endpoint. It means it is a closed interval. All right. I hope that answers your question. Is there any other question?